Okay, instruction team, we're being recorded, so pretend to be professional.
Hi, everybody who's coming in. Hi again.
Hey, everyone.
Hi, everyone.
You know, I really need an audio track to go with this slide. It would work much better with the music.
Yeah, I think it'd be cute. Hi, everybody coming in. Welcome.
All right, welcome everyone. It's 7 o'clock. Welcome to the fifth class in our unending campaign to help you pass your technician license examination. As always, we're following along exam questions in the order in Gordon West's book. A reminder, all of your instruction team, whose emails are listed on this slide, are available anytime you have questions about ham radio, about the exam, or about anything related to ham radio. Any of us will be happy to answer emails from you. This time I really am recording. Apologies to those who were counting on the recording last week. And it'll be on the XCZ.com YouTube channel, probably about midday tomorrow. As I say, this is the fifth class in the series. I'll be the technical presenter tonight, talking about a couple of issues during the introduction, programming your new HT, some details about how to sign up for the online exam, then we'll get into questions as presented in the text. Deborah this is a mistake. Deborah is not KM6SV. Deborah is, don't tell me, KM6MLK, and she'll be presenting her experience in ham radio. I'll talk to you about Ohm's law. This is good. We actually get into electronics. This will excite me, and I know many of you will be excited too. Then Karen, the real KM6SV, will talk about reporting earthquake intensities. And I'll talk a bit more about exam questions, and we'll conclude with Don, K6GHA, who will talk about the fun of radio contests. And Don is so enthusiastic, he's been known to go on at some length. So I put him at the end of the program so he can go on as long as he wants. And anyone who needs to leave at the regular time certainly may do so. And of course, as always, we encourage questions. Who, if anyone, who has a question now? Anyone have a question or comment? Okay, before I dive into the class material, I want to make one comment about sharing email addresses. You've probably noticed that the emails I send out to the class are to a blind copy list. This was to prevent sharing emails from anyone who perhaps didn't want their email address broadcast widely. But it also occurred to me that it would be useful for many of you to be able to get in contact with each other. Part of what happened in our live classes back when we could actually meet was that new hams met each other, formed friendships, and helped each other out. So I'll be sending out an email tomorrow requesting permission to share your email address with the rest of the class. If that's okay with you, just send me a reply. And those of you who agree to share your emails will get an email from me with a list of everybody else's email who has agreed to have it shared. Does that make sense? I think it might. Okay, let's get started. Any comments about that? All right, as always, I'm hoping you'll ask questions. The benefit of a live class instead of some of the excellent YouTube videos that are available is that you can actually ask questions when things are unclear. So if when I say something you don't understand, and I assure you I probably will, please unmute your mic and speak up, because if you're wondering about it, others probably are too. This frequency chart that you see on your screen, it's on page 6 in the textbook. It's not on the exam. But some people have been curious about where these ham frequencies fit in with the rest of the radio spectrum or with the whole electromagnetic spectrum. Down here, the chart goes from very, very low frequencies like 1 hertz, which are audio, all the way up to really, really high frequencies, X-rays and gamma rays. And the stuff in between here is enlarged to show the radio spectrum with the various amateur bands stuck in here. As I say, this is on page 6 in your book, and it may be of interest for you to look at it from time to time. It's not on the exam. I would encourage you to go out and get your first radio if you haven't already. We gave you our recommendations for what to buy a couple of classes ago. And what you'll discover is that there are lots and lots of useful frequencies that you want to have preset in your radio. In fact, we have a list of 127 useful local frequencies in the 2 meter and 70 centimeter band. These are lots of repeaters in the area. They are simplex channels that are used by agreements, and also public safety, fire, police, and so on, and weather channels, which are receive only. And you can enter all these frequencies by hand from the front panel of your radio, but that's really a lot to ask of a human being. Much easier is to load the information into the radio using a little software on a personal computer. So the frequency list that we're recommending is on this website. Don't need to write that down. I'll include this information in an email tomorrow as well. And to get your radio programmed, there's 2 ways to do it. You can do it yourself. And there's a commercial product, which I like, made by RT Systems, which costs $50. Or there's a free product, which is hard to use, but when you get it to work, does work, which some people like. Or as a special offer for new hams, let one of us do it. When you get your radio, if you don't want to try programming it yourself, send an email to us, and one of us will figure out a way to get with you and your radio and program it up for you. Comments or questions about that? So it's not too soon to get your first radio. I recommend your first radio is probably a handheld radio, like one of the 2 we recommended. And even without your license, you can listen. And there's interesting stuff to be heard. So talking about license, to take the license exam online, the first thing you need, in fact, any first thing you need, no matter how you're applying for a license, is to get a FCC registration number, referred to as an FRN, yet another acronym. And I have a slide that tells you how to do this in a moment. Then the next thing you need to do is read the rules for the virtual exam sessions that are on the San Benito County Amateur Radio Association website at this URL. And then email Heatherly, the ham who runs the reservation system for online exams. Her email is testing@sbcara.org. And again, I will put all of this in an email for you. So to get a Federal Communications Commission registration number, basically you go to this website and fill out the form and click submit. Basically, they want your name, address. They want to know if you're a citizen or not. And there's a few other things that they ask. It's pretty simple. And once you have that number, you're set to sign up for an exam. Anyone have questions about that?
How long does it take to get your number from them?
It should be within a few seconds. It's an electronic system.
Oh, okay, great. Thank you.
And as I said, I will send you an email with all of these links, so you don't need to scribble them down from my slide right now. And any other questions? All right, onward. So I'm going to talk now about the technical information that's alluded to in the exam questions, which are covered on pages 139 to 152 in your textbook. And I want to talk first about just some definitions. These are conventions. They're just things that you need to know. Voltage, which is the electromotive force or the pressure of electricity measured in volts, is generally designated by the letter E. I have to make an apology on behalf of physicists and engineers, the people who picked all these letters. Some of them are just arbitrary, so just go with it. So for voltage, the letter to remember is E. For current, which is the flow of electricity measured in amperes, that is conventionally represented by the capital letter I. This is the fault of Ampère, the French physicist who figured a lot of this stuff out, who referred to l'intensité du courant, and I is for intensité. But you don't need to worry, you just need to remember that it's I. Resistance, which is a measure of how much resistance there is to the flow of electricity measured in ohms, has the letter R. Capacitance, which is a measure of the storage of electrical energy measured in farads, named for Michael Faraday. The letter C is the convention for that. And inductance, the storage of magnetic energy, which is measured in henries, gets the letter L, I think, because all the good letters were taken, but that's just the letter that's used for that. So these are conventions. You'll see this lots of places when you read about electronics, and you just kind of have to know what the letters mean. Any comments or questions about that?
Yeah, I was noticing my frustration was in the pie chart, if you call it the PIE versus the ohms simplified pi. I was getting confused with P for power, trying to determine if it's watts or if it's volts, and
Yeah,
that was frustrating.
yeah, it can be confusing. Power is watts, you're right, but you get all this stuff at once, and it can be a little confusing at first. Okay, moving onward. I'm going to show you the way to connect a voltmeter to measure voltage, and then in a moment, the way to connect an ammeter to measure current or amperage. These questions might be on the test. A voltmeter basically is connected in parallel. So if we have a battery here that's feeding a light bulb, we've got current flowing out of the battery through the light bulb back to the battery. And we want to know how much voltage is on the light bulb. We take our voltmeter and we just put it in parallel. We measure it across the load there. Or schematically, here's a schematic diagram of the same thing. These funny lines are the schematic symbol for a battery. And here we've got our symbol for a lamp, and our voltmeter is just connected in parallel across it. So it measures the voltage that's across this lamp. If we want to measure current is the flow of electricity. We're measuring flow. We've got to get the electricity to flow through our meter. So we actually connect the meter in series. So here we have current from the battery going through the meter, coming out the meter, going into the lamp, and then back to the battery. Or schematically, you see we've got the meter in series with a load. If you remember that current is a flow, it's a flow of electricity, it'll make sense that the way to measure the flow is to get in the flow, to get the electricity to flow through the meter so that it can tell what's happening. Any questions or comments about that?
This, at some point, a comment of if people are feeling like they need to memorize some of this, that for a whole lot of people, visually just looking at it doesn't work very well. And so saying it out loud, writing it out, I don't know neurologically why, but if you're feeling like, I'm not familiar with this and I just really need to, no pun intended, power through and largely memorize it, looking at some schematics, reading them out loud, saying out loud, well, the voltage across this is this many, such and suches, may help it stick.
You're absolutely right, Deborah. People learn in different ways. And one of the frustrations with having to do all this over Zoom is that I mainly have to show you pictures and talk about them. When we had the live class, we would actually bring in real equipment and you could put your hands on it and measure things, but we're suffering along here as best we can. The way I'm explaining things here is a little bit different from what's in the book. So if the book doesn't make sense to you, it's possible that I might. I'm trying to try to explain the logic behind this instead of just something that you have to memorize. So the logic here again is current is flow. If you're going to measure the flow, you've got to be in the stream. You've got to be, your meter's got to be hooked up in series. So let's look at a couple of exam questions here. I'm not going to go through all of them, but I wanted to talk about a few because I thought perhaps if I explain things a bit, they might make a bit more sense. So here's a possible exam question that asks about what component changes alternating current into varying direct current signal, and that's a rectifier. So a rectifier, typically a diode, only lets electricity flow in one direction. It won't let it flow the other way. So it's analogous to a check valve in plumbing. If any of you are familiar with plumbing, the electricity only flows in one direction. So over here, we have alternating current. That means the current wants to flow back and forth and back and forth and back and forth. This is what's in our walls. Typically goes at back and forth at 60 times a second or 60 hertz. If you put a diode there, the diode is only going to let the forward stuff through. So what you see coming out of the diode, if we're plotting voltage versus time, is we only get the positive pieces. We don't get the negative pieces where the electricity was flowing backwards. And this kind of component is called a rectifier. That's just the word we use, meaning it converts alternating current to direct current. Questions about this? Oh, here's some pictures of what diodes actually look like. There's all different kinds, but these are some common diodes. So more definitions. The diode has two ends, and they are called the anode and the cathode. And that's just what they're called. And there's probably a historical reason for it, which I don't know. But the anode is the positive side, and the cathode is the negative side. And the physical components are typically marked with a band on the cathode end, which lines up with this little line here and the schematic symbol. These are arbitrary things. There may be a little logic to them, but mostly it's just a convention. So here's a fairly simple question. What component opposes the flow of current in a DC circuit? That's a resistor. They often look like this. And this is the schematic symbol for a resistor. It's just a bunch of squiggly lines which are supposed to connote resistance. You may get, these are actual questions. You may get this question on the exam. And what component is used as an adjustable volume control? If this is a variable resistor, a potentiometer is the name for that. You've seen these things. This is what the component often looks like. And this diagram shows what's going on. There's a black resistive element here that is inside, and then some kind of a mechanical wiper which moves around the resistance. So you can see as it gets closer to this terminal, the resistance between this lead and the wiper is going to be decreased. So by turning the knob, you vary the amount of resistance. And schematically, the way we show that is with the resistor symbol and then with an arrow next to it. The arrow is supposed to be like the moving element, the wiper in the potentiometer. It's a variable resistor. It's a potentiometer. They're the same thing. Two words for the same thing. So what kind of component stores energy in a magnetic field? That's what an inductor does. An inductor is just a coil of wire. And putting the wire coils next to each other cause the magnetic fields to reinforce and overlap. And there's actually energy stored in that magnetic field.
John, is there an easy way to remember the difference between a capacitor and an inductor? Like a mental trick? Because I keep getting them confused.
No, not that I know of. Sorry, that's not very helpful. I might be able to come up with a mnemonic, but offhand I don't have one.
I guess the part that confuses me is some of them store magnetic fields and some of them store like it's still
electric field.
Yeah, that's the part that I'm like.
That's the key difference. That is the important thing. Inductors are storing energy in a magnetic field, and capacitor. Oh, here's another inductor. Let me go to the next slide. Capacitors, which look like this, store energy in the electric field. In other words, there's a pile of electrons that end up on one side of the capacitor and positive charge on the other side of the capacitor, and those will sit there for some amount of time, and that's energy that's stored.
Yep.
So how do you remember that capacitors store energy in the electric field? You kind of have to learn it. This is what one kind of capacitor looks like. You may, if you look inside an old radio, you've seen these, like they're almost like bread slicers. And as you rotate the knob here, the plates mesh more and more, and that increases the capacitance between the plates.
Are there good examples of like, batteries or capacitors? And I don't know, what would be an everyday inductor that people might be familiar with it, like, oh, that's a such and such, and that might help.
Well, an everyday inductor. I don't know if you're into auto mechanics, but the spark in spark plugs comes from a coil in the car, which is nothing more than a big inductor.
Okay.
Does that help?
that helps. Yep.
Okay.
So somehow saying, I'm not going to confuse them, but of just sort of remembering the familiar thing that I know exists, even though I don't look at it every day, and then just try to match that up with the name that I don't use.
Yeah, that is a good way to learn. So let's go back to our inductor picture here. So let me talk just a little bit more about that using automotive analogy. The way sparks are generated in an automobile is battery current flows through a coil, which looks, kind of like this. It just has a lot more turns. And then the current is interrupted but there's a bunch of energy in the magnetic field. The magnetic field collapses and it keeps pushing the electrons through the wire. And because they have no place to go, the voltage gets higher and higher and higher, and then it sparks over and ignites the gasoline in your engine. So it's the magnetic, the energy stored in the magnetic field that makes the spark. That might be helpful if the automotive analogy helps. There's lots of different shapes for inductors. They're all basically coils of wire in one form or another. And just talked about a capacitor. So here's another component that the question is, what class of components uses a voltage or current signal to control current flow? That's a transistor. Schematically, we have a drawing of a transistor here. This is one kind of transistor. Transistors typically have 3 terminals, and the way these kinds of transistors work is that a very tiny current flowing from the base to the emitter here will control a much larger current flowing down from the collector to the emitter. So you use this tiny current to control a much larger current, and that's what makes amplification. If the small current controls the big current, you've amplified the signal. And transistors do that. Questions about this? On the exam, you'll see some of these questions, and they also want you to know the schematic symbols for some of these components. So we'll be going over those in a little bit. Here's samples of different kinds of transistors. These are small ones. Transistors can also be quite large. Okay, we'll go to Deborah in a moment, but first I'm wondering if anyone has any more questions about that material. Deborah, what's it like being new to the hobby? What's been your experience?
Well, I became a ham in December, and I started right away going to 2 meetings a week. The Wednesday night meeting, which is an Aries meeting, and for San Lorenzo Valley, and the Thursday night Coastal Net meeting. And that's because my main interest was in providing emergency contact in something like an earthquake, being of service. That was my main impetus. I'm not particularly wanting to put together my own rig. I don't understand enough of the radio building parts that I ever want to put together my own stuff. I'm happy with my little handheld radio, and ended up with eventually getting a nice little Kenwood setup that works either in the car or the house with a large antenna. And what I have found is that I got fairly confused at first by all the different terms that got used for what you do on the radio. So, for example, you talk to each other, you can use, I've forgotten the word already. There's simplex, which is just, you're talking on the wave and you're not getting any help. You just have to talk to somebody nearby you, or you can bounce your signal off a repeater. And so you can repeater hop, but you can't simplex hop. So I'm still learning sort of terms and how they work together. But what I really liked was the idea that all these people get together, maybe 30 people on Wednesday night and usually around 20 on Thursday night. And they all just check in with each other, and they have little games that they play to make things more interesting. And the games allow I think what happens is that the big boys sit around and they map us all and they figure out who can talk to whom. And you figure out where hills are in the way and where people can talk to one another. And at first I was just listening. And then I discovered it was more interesting to write things down. So I started trying to keep track of who was on the repeaters and who was talking on simplex. And they would have message exercises where the whole point of it is to learn how to listen and figure out what kind of messages to pass and what kind of information people want. And it turns out all of that is regulated by forms. And I wasn't at first paying attention to that, but now I print out the form and I take the message down, and I'm surprised at how difficult it is to get every word and every letter correct, but that's part of what you learn to do. I think I saw a little thing that went up, a question. Can you tell me what that question was, John? I think it was,
Oh, in the chat?
yeah, I think it was a question about how do you get the call signs, because they're hard to hear.
Oh, yeah. How do you hear call signs? Folks seem to say it so quick. How do you do that, Deborah?
Yes. Okay. So at first I couldn't do it. So first, John sent me this list. I think it was John that sent me the list. That's a list of all the people on in the group, and it has their name and their call sign. And so at first I was listening just for the last 3 letters. So I'd listen for the word 6. So I didn't have to pay attention to KN6, the I6, and K6. I only had to hear the 6 because almost everybody's a 6. There's occasional 5, but almost none. It's all 6s. And then I'd listen for the 3 letters after that, and I'd find them quick like a bunny on the list. But then I decided I should try to write them down instead of finding them on a list, because some people aren't on the list and then you're really screwed. So what I did was I started writing them down, and I would get usually 4 out of the 6 at first, and now I can get all 6. So it's a matter of letting your ear get used to it. But also when you're first the net control, they're really good about using the alphabet. And so you use this international alphabet. And so my call sign is KN6MLK, but I have written down on a piece of paper taped to the top of my radio what my call sign is, because I can't remember it because I get so flustered. But there it is, Kilo November 6, Mike Lima Kilo. And after a while, and I'm going to say it took me 2 months, I didn't hear the word Mike and the word November. I would just hear the letter M and N, because otherwise you're writing down the word November, which is no good at all. So I learned to listen for the letters and write them down. And now I can get almost always 6 out of 6. And occasionally I don't get them all. So I've got to say it's a matter of practice. And I didn't think about writing things down when I was first listening, but I will encourage you to get a notebook and write them down. So I've actually got it right here. I keep my little lists and I write them down. Oh, there we go. And they're not neat at all, but I write down a little note for every meeting that I go to, and I say what they did that meeting, whether they talked on a repeater or simplex, whether they wrote messages. And I'm going to encourage you to pick one. And there's something almost every night. If you just look up Santa Cruz Amateur Radio, this website comes up and it lists all these different things going on at different times of day and night, and you can listen. And occasionally I just turn the radio on. I don't do it very often, but sometimes when I'm painting in the room next to the radio, I'll listen to it. And if somebody puts their call sign out, I'll actually go in there and say hello. I don't do it very often. Sometimes they tell me they don't want to talk, they were just testing, but they never get mad when you say something to them. So I think that's a good thing. So that's all I've got.
Yes. Thanks very much, Deborah. Who
Sure.
has questions or comments? I appreciate your perspective. It's just so you know, I've been doing this for a long time, and sometimes I can't get the call sign straight either.
Good. I'm surprised at how far away of some of them are. So we get somebody from Salinas now and then in Monterey.
Yeah, and then if they check in via
Oh,
the
and the
IR,
space shuttle. There was somebody in space that talked one time. And I thought it was a joke, but it wasn't. A space station thing?
there are hams on the International Space Station, and they have ham radio equipment. And when they're not busy, they talk to amateur radio people. So you have to kind of get lucky. But absolutely, it's possible.
Anyway, I've been enjoying it, and I didn't think I would particularly enjoy it. I really did it to be of service, but it turns out I kind of like it. So there you go.
Cool. Thank you.
You bet.
And you guys will all like it too. Take it from me and Deborah. Okay, let's go back to some exam questions.
Okay, I'm all done. Wanna listen to the rest?
You have to mute your mic now,
Oh.
please, Deborah. Thank you. Okay, these are questions from pages 153 and on in the text. And yeah, one of you alluded to this, these magic circles that the text uses. I'm not a fan of this technique myself, so I'm going to explain this material in a different way. If you like this remembering formulas using this this little mnemonic, please go ahead. It just has never worked for me, so I'm going to explain how to answer all the exam questions without using these magic circles. And what you'll use instead is just a little bit of 6th grade algebra. And I know all of you passed 6th grade, so this won't be too hard. So let's just look at a couple of useful formulas. Power is, it's a measure of how the rate at which energy is used. Power is measured in watts, and watts electrically is equals volts times amps, or using the letters, power equals E times I, E being electromotive force or voltage, I being l'intensité du courant, or intensity of the current. So this isn't too hard. You can remember that power is volts times amps. So just think about this for a minute. You guys probably all know that the power in most of our houses is 120 volts AC. We used to have inefficient incandescent light bulbs, 100-watt light bulb. It would be drawing about 1 ampere at 120 volts. If it actually drew a whole ampere, it would be a 120-watt light bulb, because it'd be volts, 120 volts times amps, 1 would be watts. Anyway, that's a formula to remember. It's called watts because of physicist James Watt, a really smart Scotsman who figured out a lot of this stuff in the late 18th century. So there's a bunch of problems now that use basic arithmetic, and don't be scared. You guys can do this. So here's a sample problem. How much power is being used in a circuit when the applied voltage is 12 volts and the current is 2.5 amps? Well, gosh, you remember that power equals volts times amps, right? So we've got 12 volts, 2.5 amps. You don't even need a calculator. 12 times 2.5 is, well, 12 times 2 would be 24. So it's got to be a little bit bigger than that. And look at the answers. There's only one answer that's a little bit bigger than 24, 30 watts. Any questions about this? There are, I don't know, half a dozen or so problems like this. You might get one on your exam. Let's look at another one. How many amps are flowing in a circuit when the applied voltage is 12 volts and the load is dissipating 120 watts? So now we're given volts and watts. Well, we know that power is volts times amps. So we can, if we can divide both sides of this equation by the volts by E. So current is going to be equal to power divided by volts. Everybody see how to go from here to here? If you can remember this, you don't need to remember the little pie drawing. But if you like the pie drawing, it will tell you that current equals power divided by volts. So in this case, 120 watts divided by 12 volts is 10 amperes. That's how you solve all these classes of problems. Questions?
You know, for clarification, I was just remembering my old college days, and you know, the pi, or the 3-part pi, the horizontal line was division, down and then across the bottom was multiplication, right?
Does that work for you, Jeff?
It's starting to remind me how to do it, yes.
Great. That's its purpose, is to remind you how to do it. And if that's working for you, then go with it. Absolutely.
Yeah, I wasn't sure if other folks had the same issue with the circle and the horizontal line and the vertical dividers. Thank you.
Okay. Second useful formula: volts equals amps times ohms. E equals IR. E equals electromotive force. I is current. R is resistance. This is known as Ohm's law, and of course it's named for Georg Ohm, another physicist from the early 19th century who figured all this stuff out. So if you can remember the second formula, E equals IR, you can solve a whole bunch more problems. So for example, what's the voltage across a 10 ohm resistor if 2 amps is flowing through it? Well, volts equals amps times resistance, right? E equals IR. 2 amps times 10 ohms would be 20 volts. All right, you'll probably get 1 or 2 questions like this on the exam. Well, before I go on to series circuits, are any questions about this?
Oh, again, sorry to turn. And some of these sort of multiple choice test pro tip of, if there are no formulas that involve addition and subtraction, you can kind of lock out 8, the 10 minus 2 is not relevant because that's addition or subtraction. 12 isn't going to be relevant because that's adding or subtracting. So the Kaplan test taking strategy of, if you can knock out some just being obviously garbage possibilities.
Absolutely. Yeah, there's yeah, I don't talk too much about test taking strategies. I am happy for you to use whatever works for you to get through the test. My hope is that you will not just pass the test, but you'll actually learn some of these concepts, which will be useful to you when you play around with the radio or want to do just a little related work. But yeah, whatever works.
And some of this is just test anxiety. People tend to perform on tests so far, or people get nervous.
Yeah.
they forget most of what they would know in day-to-day life. So
Yeah, some people do well on tests, others have trouble on tests, unrelated to the depth of their knowledge of the subject. It's really true. But we're here to help. So when something is confusing, we're hoping that you ask about it, either ideally in class or maybe later. Okay, couple of concepts that are key that you need to know about, and they're again definitions. A series circuit. A series circuit is shown in this example here. We have a battery, we've got 3 resistors, and they're connected in series. This is what the word series means when you're dealing with electronics. So if you think about it for a minute, if there's current flowing from the battery, it has nowhere to go except around this loop, right? There's no other place for the current to flow. You can imagine current flow being water through a pipe if you want. And the current flows, from the battery through the resistors and back to the battery. So the key concept then is the current has got to be the same in each of these resistors. Each element in a series circuit has to be getting the same current because there's no place else for it to flow. So it might be that these resistors are all different values. That doesn't matter. The principle is still whatever current is flowing is going to be the same in all of them. The analogy and an analogous concept is a parallel circuit. Here we've got current coming from the battery, and it's divided among these resistors. The current is going to flow through one or the other or another resistor and eventually go back to the battery. But the currents through each resistor might be different. You can see there's different paths for the current. And the way in this example, the resistors have different values. So the lower resistance is going to allow more current to flow through it. The thing that's the same though for a parallel circuit is the voltage across all the parallel elements is the same. And you can kind of see that from the diagram. If these conductors are presumed to be perfectly conductive, so the voltage has got to be the same across all 3 components.
I have a question on that slide.
Yeah.
So the R1, R2, R3, does it always go larger to smaller as it's closer to the battery?
No.
No, okay.
This is an arbitrary example. So in a circuit, typically the components are identified with a letter for the component type, R for resistor, and then they're just numbered sequentially however many resistors there happen to be. And there's no relationship between the resistor designated number and its value. That's just a convenience.
What determines the value?
The design of the circuit, what the circuit is supposed to do. This particular circuit doesn't really do anything except the resistors get a little bit warm. So it kind of, I guess the circuit is just designed to run the battery down. Not terribly useful. Excuse me. But the principle here, the reason I'm talking about this is there are several questions on the exam that ask you about series circuits or parallel circuits. So that's a key concept that I want you all to learn.
Good.
And that's all the talking I'm going to do about this series of questions. You need to look at the questions on your own, but if you can apply the information from the couple of slides I just showed you, you'll be able to get the questions. But does anyone have a question about that, or is there a question in the book that seems confusing? I'd be glad to talk about it if there is. we do depend on you guys to, to read the material, ideally ahead of the class, because we did run this class once where we went through every single possible question, and I got lots of believable feedback that it was totally dull, dull, dull. So we're not we're not doing that. Okay, if there's no questions, then Karen, would you talk to us about earthquakes, please?
I would love to talk about earthquakes, but I'm not going to talk directly about earthquakes. I'm going to talk about how we measure earthquakes. So we're all used to the Richter scale, which is a measurement of earthquake magnitude. There's something that geologists talk about when it comes to earthquakes that's related to, but somewhat different than magnitude, and that's intensity. And intensity when it comes to earthquakes is a measurement of what the impact of the earthquake, the effect of the earthquake is on the Earth's surface, as opposed to the magnitude of the earthquake. And why is this important? Well, and what's it have to do with ham radio? So one of the useful things that a ham radio operator can do in an earthquake is provide what we call ground truth, which is information to our local officials about what's really going on in various parts of, in our case, the county. And the easy way for us to do that is to all be using the same scale of intensity. Our county officials, they don't care what the magnitude of the earthquake is. They don't care if it's a 2.0 or an 8.0. They care how bad's the damage. And more importantly, what type of damage is in different parts of the county so that they know what type of response to bring about. So in the US, the USGS has declared that we will use what's called the modified Mercalli intensity scale to measure intensity of earthquakes. And the nice thing about the scale is it also makes it really easy for us to quickly gather data from a lot of ham radio operators about how intense the earthquake is in various parts of the county. So this scale measures from 1 to 10, from not felt at all, basically, to basically total damage. Buildings are completely knocked down all over the place. We only measure it when we're taking reports of earthquake intensity over the radio. We only measure from 1 to 8, and we lump 9 and 10 in with 8 because the response from our county officials is basically the same whether it's 8, 9, or 10. So I can give an earthquake report in about 5 seconds using this modified Mercalli intensity scale. And you'll be able to do the same thing as soon as you have your license. Kilo Mike 6 Sierra Victor, Mike 4, Glenwood, Kilo Mike 6 Sierra Victor. And that tells somebody who's listening to me that I'm in the Glenwood area of the county, and Mike, which is the phonetic alphabet for MM, which is the abbreviation for modified Mercalli. I had a Mike 4, so a modified Mercalli level 4 in my area, which means that the earthquake was felt indoors by many, outdoors by a few during the day. At night, some awakened, dishes, windows, and doors were disturbed, walls make cracking sounds, sensation like heavy truck striking building, standing motor cars rock noticeably. That's a lot more clear and concise and easier to tally than it is for me to go, oh my God, everybody, there was an earthquake, and oh, my dishes rattled, and my walls made a cracking sound, and what do I do next? So we use this Mike scale. And it's great. We practice with it sometimes on our weekly nets, and I encourage you all to become passingly familiar with it, but also we know you're not going to memorize this. We have little wallet cards that a lot of us like to carry around that have this Mike scale on them, so that when there's an earthquake, because we know it's when, not if, we'll be able to easily and quickly give a concise report of the intensity at our location. Now, there is, before I move on, is there any questions about this so far?
When you state communication with the county, are you talking to SCZ or SCU, or are they both on the same system?
So I'm talking about Santa Cruz County, the Emergency Operations Center. But Santa Clara County uses the same modified Mercalli reporting that we do here in Santa Cruz County.
Thank you.
Any more questions?
Yeah, do they put out anything afterward of what you should, let's say it was a 5.0 and you thought it was extreme, but do they kind of put out anything to correct people? So I don't know, does that make sense?
Well, you're not wrong. If you thought that it was a Mike 10, because that's what you observed in terms of damage, it doesn't matter if it was only a Richter scale 5, you're right, because they're measuring two different things. So one's measuring what the effects are, and the other's measuring this magnitude, this that we assign a different type of numerical value to.
Right.
Okay, yeah, that makes sense.
The intensity scale is going to be different depending on your geographical location from the epicenter too. So
it's going to be different depending on your geographical location from the epicenter. It's going to be different depending on the geology of the ground you're on top of. And to some extent, it's going to be, it's a little bit more wishy-washy. We try to make it as precise as possible, but, I might be standing right next to you and I might think it's Mike 5, you might think it's Mike 6. We might both be right. And in your house, maybe it was a Mike 6 and you're my next door neighbor, and in my house it was Mike 5. That happens. But you'll get an idea of what it is. You'll find that various geographical areas tend to fall within a range, and therefore the county knows this area was hit hard, this area wasn't hit. And then they also might find out, like, you might not hear any reports from the Loma Prieta area of the county, and that might be because they didn't feel it at all, so nobody bothered getting on the radio. And that might be because they're experiencing a major problem from the earthquake and nobody could get on the radio. So we get some information based on the geographic distribution of the reports, even if we don't have numbers attached to them. More questions?
It's a question in the chat, Karen. Say more about why you call it Mike.
So Mike is the phonetic alphabet for the letter M, and the abbreviation for modified Mercalli is the letter M twice. So in ITU standard phonetic alphabet, that would be Mike. And so we call it Mike. So if there's no more questions about this, I'm going to move on to a slightly different form of earthquake reporting that you can also do as an amateur radio operator. So this is also from the USGS, and this is a form that's from their Did You Feel It system for earthquake reportings. You can do this over the internet if you have internet available. And this form goes down and asks a bunch of questions. And if you happen to be familiar with the modified Mercalli scale, the questions might sound a little familiar. Like, did dishes rattle? Did you hear creaking from the walls? But what happens if, well, there's a problem with this form. Namely, in major earthquakes, internet goes down and they don't get any reports out. Well, about a year ago, I think it was, amateur radio operators got together with the USGS and came up with a partial solution. And that is that we've attached the Did You Feel It form to the WinLink amateur radio email system. So you can submit a Did You Feel It report via amateur radio through the WinLink system. And I am happy to help you figure out how to do that once you get your license, if you're interested in doing that. And so they can start getting reports from inside areas where internet has gone down. So I encourage you, if you experience an earthquake after you get your license, hop on the radio, give a mic report, and also get online if the internet's up, or on WinLink if the internet's down, and file a Did You Feel It report. And that'll be very helpful. Thank you. Any questions about any of that? I think it's back to you, John.
Okay. Thank you, Karen. All right, back to exam questions. Covering now the possible questions that are on pages 159 to 170 of the text. And this section mainly relates to recognizing the schematic symbol for various components. And these schematic symbols make a certain amount of sense, but they they're just symbols, so there's a certain arbitrariness to them as well. Why are stop signs octagons? There's nothing octagonal about stopping at an intersection, but the symbol for a stop sign is an octagon with the word stop in it. Well, these are symbols kind of like that. So here's a question. Component 3 in the figure. Well, here's the figure. Component 3. Inductors are these kind of curvy, squiggly lines. And any component that has an arrow, a third connection with an arrow on it like that, indicates it's variable. It's like the slider in a potentiometer. So this is a variable inductor. Now, what might a variable inductor actually look like? Well, here's a couple of pictures. Typically, it's a coil of wire with connections that you can make partway through the coil. So you could connect here or here or here. You could vary the inductance you have by connecting to different parts of this component. Here's another question. What's this thing here? Well, that's the symbol for an antenna. How do you know it's an antenna? Well, I'm telling you, and it's always drawn kind of sticking up in the air if the schematic's drawn right, and it will be on the exam. So this is an antenna. Real antennas look, kind of like this, or maybe like this. Antennas can be all different sizes and shapes. The schematic symbol is this, this triangle thing. So how do you make a tuned circuit? What do you need an inductor and a capacitor. How do you know that? Well, you know it because I'm telling you, I guess is how you know it. Inductors and capacitors hooked together like this form a tuned circuit. Well, what's a tuned circuit? A tuned circuit is a circuit that resonates at one particular frequency. So this kind of a circuit would be in the radio receiver or in the radio transmitter, and it would allow the circuit to preferentially get signals of a particular frequency and to reject signals that were not of that particular frequency. That's a tuned circuit. And the important thing to remember here is that the exam question is that a tuned circuit is an inductor and a capacitor. And just to confuse things, sometimes the exam calls them coils and sometimes they call them inductors. An inductor is a coil of wire, so they use those terms interchangeably. Any questions about this? Okay, more components. Item 1 here, the little jaggy lines, those are resistors. These are photographs of actual physical resistors. Resistors are often that have their value indicated by colored bands. And if you get into building circuitry, eventually you memorize the color code. None of you need to know that, but you just need to know that the jaggy line here is a resistor. So here's another schematic symbol. We saw this already. This symbol is one kind of a transistor. And the exam question actually asks you what it's for. What does it do? Well, transistors control current or voltage. So the transistor allows a small signal here to turn on or turn off this light bulb by running a large current through the transistor. Component recognition. All right, this thing here is some kind of a lamp. Here's a picture of a lamp. This is like a flashlight bulb back when flashlights all had incandescent bulbs. This is the circuit symbol for that. If you're good at visual memory, you'll have no trouble with this. If you're not good at visual memory, the FCC would still like you to learn this. And this symbol here for item 4, short and long lines like this is a battery. Batteries are often made up of multiple cells in series, and that's what this schematic symbol is supposed to indicate. Just look at these and get familiar with them. You'll probably get 1 or 2 of these questions on your exam. And if you have a general familiarity, then your guesses will be good. If you're not sure exactly yourself, which is the right answer. Okay. Now they're asking about a switch, component 3. This symbol here is a switch, and you can imagine it as this little line either connects the circuit together or it's open and the circuit is not connected. But they ask you about this single pole, double throw stuff. And let me tell you what this terminology means. Yeah, the answer is it's a single pole, single throw switch, but why is that? So here's the switch from the previous slide. Single pole, single throw. If it were single pole, double throw, that would mean there's only one moving part, that's the pole, but it could connect to two different circuit elements. So here where we're single pole, single throw, there's only one connection we can make. Double throw means there's potentially 2. If you and your sibling, when you were young, did what I did with my siblings, and one stood at the top of the stairway and the other stood at the bottom of the stairway, and each of us had a switch that worked the same light, and you could turn the light on or off from the top of the stairs or the bottom of the stairs. And so we would have a game where one of us tried to keep the light on and the other tried to keep the light off by furiously throwing the switches back and forth until our parents made us stop. Anyway, those switches were double throw. That's why the switch could control the light from either the bottom or the top of the stairs. If you have double pole switches, that means there's two moving elements that's shown schematically here. And here's double pole, single throw, and you can have double pole, double throw switches. This is just more electronic jargon. More components. What is component 4? This guy is a power transformer. It's 2 inductors and some iron in between. That's what this is supposed to show. And if this were a live class, I'd pass these things around so you could hold them, but best I can do now is show you pictures. These are examples of power transformers. They basically consist of lots of turns of wire and some iron. Questions about any of these components so far? What is a relay? It's an electrically controlled switch. It's a mechanical switch that is opened or closed by a current passing through a coil. When you run current through a coil, it creates a magnetic field, and that can be used to pull a piece of metal that flips a switch. And when you build a thing like that, it's called a relay. Here's a close-up picture of an actual relay. Here's a big coil of wire. That's an inductor or an electromagnet, same thing. When current is run through this wire, there's a magnetic field that pulls this thing down toward it, and that closes these two switch contacts. This is what a relay is, and the FCC wants you to know that. Here's some pictures of different kinds of relays. They're often packaged in a little plastic envelope. Sometimes you can look inside and watch it work. Several semiconductors and other components in one package. That's an integrated circuit. We've all heard about integrated circuits, sometimes abbreviated as ICs. And that's a simple definition. All right, before I talk about decibels, anyone have any question about this component identification stuff? You kind of have to look at it and just get familiar with it. All right, let's talk about decibels. Decibels are useful ways for comparing power measurements. Decibels are logarithmic units, but you don't need to know too much about them. They're a useful way of comparing two power levels. So if you have something that is uses twice the power of something else, another way of saying that is that it uses 3 dB more power. dB is an abbreviation for decibels. If something uses half as much power as something else, its power output is minus 3 decibels compared to the other item. So plus 3 is twice as much, minus 3 is half as much. If something uses 4 times as much power, it's 6 dB, uses 6 dB more power. So plus 6 is 4 times the power, minus 6 dB is 1/4 the power. Plus 10 dB is 10 times the power. The good news is this slide contains everything you need to know about decibels in order to pass the technician exam. Why do we bother with this? Because it's a very useful way to compare power levels that are greatly different. If you think about the power coming out of a transmitter, that might be 100 watts. And then you think about how much power actually lands in a receive antenna across town by someone who's listening to that radio station, it's a very, very, very tiny fraction of the power that comes out of the transmitter. And the convenient way to measure the difference in really in numbers that are really far apart is to use logarithmic units. That's why we use decibels. They end up being convenient in lots of ways. There's questions about them on the exam, but if you can remember these little facts here, 3 decibels means twice as much, -3 means half as much, 6 is 4 times, -6 is 1/4, 10 dB more is 10 times the power. These facts will answer all the questions that you're likely to be asked on the exam. Questions about this?
I was always under the impression that the decibel was a unit of emitting sound.
We use decibels to measure sound as well, and it's exactly the same principle. Sound is often measured as sound pressure level. So it happens that when you're talking about measuring sound in decibels, you're comparing it to what is universally defined to be the threshold of human hearing, which happens to be 20 micropascals. So when we say a certain sound is 80 dB, we mean it's that many times louder than this threshold of human hearing. That's in acoustics. Here we're talking electronics. We're usually measuring power in watts, or we express the difference between two items in decibels if it's useful. Good question. All right, onward. Okay, so here's a sample exam question. So 3 watts is 1/4 of 12 watts. So 1/4 of the power is a decrease of 6 dB. So power decrease from 12 watts to 3 watts, that's a change of -6 decibels or -6 dB, right? So if you just remember the stuff on this slide, you can answer all of these questions. So leaving decibels, now there's just some electronic jargon that that you're asked to learn. What is an LED? This is fairly common now that LEDs are light emitting diodes. Here's pictures of some small ones. Sometimes these things last a long time, but if you put too much voltage in them, you can burn them out, and then they become a darkness emitting diode or a dead. That's just a little ham humor, which I guarantee you is not on the exam. Here's some useful information. Multiplier prefixes. You will get questions about this. There are prefixes which indicate something is bigger and other prefixes which indicate something is smaller. Most of these, or some of these are familiar. Kilo something means it's times 1,000. Mega is times 1,000,000. Giga times 1,000,000,000. Tera times 1,000,000,000,000. Each one of those moves three more decimal places. Going smaller, if we have the prefix milli, that means it's divided by 1,000. Micro divided by 1,000,000. Nano divided by 1,000,000,000. And pico divided by 1,000,000,000,000. Some of these may be unfamiliar. You do need to learn this because component values and frequencies, other useful things that we measure, typically involve these prefixes. So here's a question. We're comparing kilohertz and megahertz, right? So there's 1,000 kilohertz and 1 megahertz. Go back to the slide here. Kilo, mega, they're different. Each of these is different by a factor of 1,000. So 2,400 kilohertz equals 28,400 kilohertz equals 28.4 megahertz. Right? Anybody have a question about this? Just a few more examples here. How many milliamps in 1.5 amps? Right? 1 amp is 1,000 milliamps. So 1.5 amps must be 1,500 milliamps. We're typically, very often in electronics, we're talking about very small currents, and ampere is actually quite a lot of current. So we're often talking about milliamps or microamps. Okay, here's just a random bit of knowledge that you will pick up here. What's a cold solder joint and how do you tell? So what are they talking about here? A lot of electronic components are put together by soldering. Soldering melts a bit of this low melting point metal, and it ensures a good connection between the component lead and the rest of the circuit. And if, while the solder is still liquid before it's hardened, if the joint is mechanically moved, then you get something like this, where there might not be good electrical contact with the component. And this is referred to as a cold solder joint. And you can recognize it. It has a grainy or a dull surface. Just a random bit of electronic lore. This is useful if you've got a piece of equipment that isn't working right. Sometimes you can fix it just by carefully inspecting all of the connections. And if you find one that looks like this, heat it up again with a soldering iron and make it into something that looks like this, and you might have fixed your problem. I've fixed things by doing exactly that. And this question wants you to know that a very large capacitor, which would hold a large electrical charge if it were, if it could take a while to fill up. If you're measuring the capacitor with an ohm meter, the way an ohm meter tells how many ohms there are in whatever it's measuring is by putting a very, very small current through it. And if you put a small current into a large capacitor, the capacitor will slowly charge up. And the ohm meter, meanwhile, will notice that the current it's measuring is decreasing. And so the number of ohms it indicates will increase. I wouldn't worry about this too much. This doesn't make much sense until you actually get to do it. And I can't have you do it over Zoom. So if this seems confusing, I suggest you ignore it. You probably won't get the question on the exam. And if you do, you can take a stab at it. And anybody have any comments or questions about this? Okay, so that's
I have a question.
Oh yes, please go ahead.
It's kind of a basic question, but I don't know the answer. What's the difference between electric energy and electromagnetic energy?
None.
Okay.
It's really the same thing.
But then,
we try to use the terms that were on an earlier slide to be so that we're precise about what we're talking about. So you can talk about voltage or current. Those are things that you can measure that relate to the total amount of electric energy that's involved.
But then you have an inductor and a capacitor, both storing energy, one being electromagnetic and the other being electric, as they're defined in the book.
True.
So what's the difference between an inductor and a capacitor?
Well, they're both storing energy. You're right about that. There are important differences between them. The inductor, the inductor has a magnetic field that it is created by the current flowing through it. And the way the inductor works is if the current suddenly stops, that energy in the magnetic field as it's collapsing forces current to continue to flow. And if there's no place for the current to flow, the pressure just builds up. The pressure is measured in volts. And so you get a very high voltage briefly coming out of the inductor. Capacitor stores electrons in it, stores actual electrical energy in it. And if you, the energy will sit there forever if it's a perfect capacitor. If you connect it to a circuit, the energy will flow out and be gone. It's kind of like a little battery in that sense, although the battery is electrochemical and the capacitor is just storing the electrons. I don't know if I've clarified things at all for you with that answer.
I guess so.
Cheap, vague answer, at least in my experience of just working with physics people and whatnot, of that there's always that physical relationship between, you know, electric current and generating magnetic fields, but people seem to not say the magnetic out loud or write it explicitly unless they are very deliberately exploiting that relationship. So I think you're more likely to see the magnetic mentioned when that magnetic field is part, you know, it's going to be there whether you want it there or not.
Absolutely right.
Really being a key exploited aspect of it, then it's talked about out loud.
What's confusing is that when they talk about inductor and capacitor in the book, the only difference I could see was one was called electromagnetic energy and the other one was called electrical energy.
I think the book is sometimes a little confusing.
Yeah.
So I guess I would agree with you that that's confusing. It's let's see, there's a mechanical analogy. Maybe this will help. There is, if you think of a pendulum swinging back and forth, when the pendulum is at one end, it stops moving, but it has potential energy, right? It's going to swing back, but at the instant it reaches the end of its swing, it's not moving at all. Then when it swings back down to the bottom of its arc, it's moving as fast as it's going to move, but it doesn't have any more potential energy. It's not going to go any lower than the bottom of its arc, but it's going to continue with its inertia to swing up to the other side. So the analogy there, the motion, the kinetic energy is analogous to the current flowing in an inductor, and that's what the magnetic field is storing. The potential energy is the voltage sitting across a capacitor, and it wants to flow somewhere, but it's just sitting there at that moment. That might or might not help.
I won't get too bollock stuff in it.
This is great. I love these questions. Anyone have more questions? Okay. The good news is that's all the exam questions we're going to cover tonight, and we're down to our last speaker, who is Don Taylor, K6GHA. Don does many things with ham radio, but I think the thing he likes best is participating in various radio contests. So I asked Don to come talk to us about what a contest is and how they work and why he likes it. Don, take it away, please.
Thank you, John. Good to be here this evening. You've had some great questions tonight. I've been pretty excited listening to them. And also the presenters, they've been very widespread and diverse and have a lot of good information. One of the things that's really, oh, by the way, I am wearing my appropriate shirt. That it's it's the law, it's the Ohm's law shirt. So it's kind of funny that I started out with ham radio a little bit different probably than most of you. My dad tried to get me involved in ham radio for 50 years, well, 40 years. And I kept saying no, even though when I first left the nest, I went into the military and was a radio repair tech. But I didn't get my ham radio license. I made my first radio contact from Okinawa, Japan to Travis Air Force Base, sitting in a back seat of a F-4C reconnaissance jet from the ground in Okinawa. So I was already involved in amateur radio in a fashion, but I just kept denying myself getting my license. What happened is I finally got my license, joined the club, the Santa Cruz Club, and met all of these people my dad had introduced me to over the years. And it was absolutely fantastic. They were saying, well, how come it took you so long to get here? Well, I took the tests, passed the tests, and joined the club. And I said, what am I going to do with amateur radio? How am I going to learn about this? What do I really want to do? And I started out like a lot of you will start out with an FM handheld and used the repeater and kind of got used to talking on the radio and doing those kind of things. Then I kind of graduated a little bit and enjoyed talking so much that John invited me to be a presenter. No, that happened later. I actually really enjoyed the idea of giving back to the community. So I became involved in ARIES, and you've heard a little bit about that, an emergency services activity. That's where I started to learn things like the phonetic alphabet and learning a little bit more about what you can do with IRLP. That's a different type of communication between repeaters and different types and modes of operation. Well, in this, I was introduced to different groups and different organizations, and one of them was called a Hamvention. And the Hamvention, that was held here locally, introduced me to things that I had never even thought about. Things like that was discussed this evening, talking to someone on the International Space Station. I actually did that. I have a QSL card with that person that I talked to. I followed up when he returned to Earth with a correspondence to him. He sent me a photograph of himself signed to the astronaut, and I have that framed with a QSL card in my office. That led to some other things. I built a few things. I built a couple of different antennas. I've started to do things a little bit outside what normal people do and aspire to do. And then I got really intrigued with something called radio sport. So I'm going to get into the presentation now and talk to you about what contesting is, but it's just another form of radio communication, but it's done very fast, and it's done in a defined period of time, and it's done for the fun of it. I'll start out by saying that. So let me go ahead and share my screen and get into the presentation here. Let me know when you see that. Are we good, John? Give me a thumbs up.
You are good.
Excellent. Oh, got it. Super. So my question is, why contest, and what is contesting? And what do you need to know if you want to get into contesting? Right now you're going, my head is swimming. I have so much stuff I've got to learn just to get my license. What am I going to get out of this, and what am I going to do with it? Well, I'll tell you, it took me a few years to get to the point of I decided to start contesting. But once I got the bug, it was pretty substantial. What you're seeing here is actually back in 2017. I went over to Friedrichshafen, Germany, let me see if I can get a pointer up here. Oops, there we go. Let me do a laser pointer there. With this gentleman, and his name is Bob K6XX, Bob Wolbert. He happens to be one of the top contesters in the United States, and it's amazing because he just lives right up in Ben Lomond. Ben Lomond, on top of Ben Lomond Mountain, in fact. And another guy who I happen to meet through amateur radio, who actually used to own Santa Cruz Electronics. And I used to go into Santa Cruz Electronics with my dad when I was a little guy to buy stuff because my dad was a radio repairman. And this guy I met, Tom KW6S, through his ownership of Santa Cruz Electronics, and then he knew my dad really well. That's how I knew it. This gentleman here is our host over in Germany. Uh, 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 Lars, and he was nice enough to bring us out and to show us around Friedrichshafen. And then the following year, we came back and we did some contesting. So let's get into the presentation here. Got to quit beating around the bush. Why contest and what's the agenda here? Well, every weekend there are contests going on, and so the weekend forecast for any given weekend is ham radio contesting with a chance of coffee. And boy, I got to tell you, coffee is definitely your friend. But why contesting? Well, what you have in contesting is you have a log that you keep. Matter of fact, in any type of radio activity, you should be keeping yourself a log. And the log is for all your contacts around the world. It basically helps you map all the things that you've done, helps you, yeah. Helps you fill out a lot of different things, and get you going in logging and making sure that you're keeping track of your FCC obligation of making sure you're keeping track of your calling distance calling. But why contest? Fun, and more fun, in my personal opinion. There's a section of contesting called radio sport, and we'll talk a little bit about what that game is, and then the 5 things you need to know if you're going to get involved in contesting. So, basically, I'll talk a little bit about once you get involved in contesting, what you need to do to optimize your success, what things that you really should know, things that are going to come to you in any form of amateur radio, and really, most of that is just practice. And then where you can find out more. And where you can find out more, not only about contesting, but about amateur radio as well, and some of the things. So we're going to go through a whirlwind thing here in the next few minutes. And I apologize if I'm going to go over because I'm way too enthusiastic about this. What you're seeing over on the right-hand side is on a 100-watt light bulb out of my shack. I worked every little red dot that you see on this map, all the way over into Japan, into China, down through Indonesia, into South America, into the Caribbean, and then across the United States and up to Alaska. I did that in 1 hour on a contest weekend. So all of these got logged in 1 hour. Those are sideband contests. So I actually talked to each one of those people, and we'll talk a little bit about what that means. Basically, this is what is known as DXing, or distance exchange. And it's the whole idea of that is the goal is to capture as many of these DX stations as you can and fill out your log and get certificates for doing that. Now, these guys are known as rag chewers, or somebody that talks a lot, like me. But in a contest, I'm much briefer. You may get my call sign. You may get some information like a signal report, but that's about all you're going to get out of me in a contest. I'll be in and out and log you and move on to the next one. So it's a speed test. So DXing is a little bit, a chance to fill out your map, see how far your signal can go, and do those kind of things. So that's the second part of it. Also, there in ARRL, they have something called worked all states. And in a given contest weekend, you can do that. You can work all 50 United States 50 of the states in the United States in less than about 5 or 6 hours. If the propagation is good, you're on the right bands, the contest is good, it's a lot of fun, and you can just bang through those, and you can get a certificate in the mail that says you worked all states. Then what you do is you search for worked all states on multiple bands. But let's talk a little bit more about contesting. Why contest? And I like to use abbreviations like FAST. It's fun. It's an activity where you can go and make as many contacts as you can with other stations in a certain amount of time. And it's the whole idea is to maximize your score. It's also about awards, certificates and plaques you receive, peer acknowledgement, and it basically what that is more than anything. It's an acknowledgement of your proficiency. The more proficient and the more efficient you get, the more contacts you get in your log in a given period of time, the more opportunity you have of winning contests. Then there's skill involved. It helps you improve and develop your skill as an operator. You heard it earlier today, earlier this evening, with the person who was talking about learning your phonetics. Kilo 6, Gulf Hotel Alpha. November 6, Quebec X-ray. You learn that and it kind of rolls off your tongue from a phone contest, but you're also doing things that may interest you once you get your license of going into things like Morse code, or even better, digital, because there have been some really amazing things in the last 5 years in digital radio that allow you on less than 5 watts to talk all the way around the world. And that's called FT8. But I can't digress because I just don't have enough time to talk about it. But there's different modes of operation, and this is to develop your skill. The last one is technology. This gives you the opportunity to learn about current and developing activities in amateur radio, but also about what you can do with your station and how you can add functionality to your station to make things better and applying technical advantage, basically. Efficiencies of, hey, is my antenna tuned correctly? That the dB gain, or the dB that he was talking about in tonight's presentation, is marked in dB gain. So if you have an antenna that is a dipole and you're out there and you've got a 100-watt transmitter and you're transmitting and its efficiency is 1-to-1, you're getting on a good night 100 watts out of your antenna. But if your antenna is a Yagi, you can increase that almost triple with a 3 dB gain, or as you said, a quarter or half, by having a 3 dB gain and using that same 100 watts and being more efficient at receiving and transmitting your signal. So it narrows the focus and it pushes all that energy in one direction. That's the benefit of a Yagi versus a dipole. Okay, but for me, it started out, it definitely wasn't all about the awards, but I'll tell you what I've done a little bit. There are digital awards, and I've been a Pacific Division winner in the past. I've worked with team awards, which is really cool because then you start teaming with others and you compound your skill and your scores, and you become you team your total scores with everybody else in the country. And we won a technical award, a team award. I've done different ARRL sweepstakes awards. These are supported by the NCCC. Also, they have what they call QSO party awards, which are each state or groups of states have these party awards. Now, I'm gonna keep showing you a couple of things. Some of these are fun. I actually had got to know and the manager of the award committee for the Hawaiian QSO party. He used to live here. He moved over to Hawaii, and I was able to send him this picture, and he got a big laugh out of it. This is from down on Steamers Lane. This is our local surfer guy. Against their award, they sent a teak award for that. There are certificates that you get from a worldwide contests, and there's something called QSL cards. QSL cards are cards that you can exchange with people. They aren't awards, but they're an acknowledgement of a contact. And you get these from around the world. And they're fun to do too. Again, this is on HF mostly, but you can do this on VHF and UHF as well. All right, so let's move on and oh yeah, my little awards guy, he's happy. And then again, let me talk to you a little bit just about radio sport. It is that it's a game, and it's a term used in ham radio to talk about the contesting, but it is really focused on one contest, and that's a WRTC. The WRTC is a worldwide contest that takes the best of the best and puts them for 24 hours in a contesting situation. When you get put into that contest situation, you're representing your country, and it's like an Olympic award event. And so the person that I talked to about before, Bob K6XX, is one of the top contesters in the world. He's ranked 17th in the world in the last WRTC that was held. But there are different games that can be played. They're not just the big games, there are little games. There's individual or team competitions. There's power competitions. Low power, 5 watts or less, your night light type of power. Low power, under 100 watts. High power, under 1500 watts. Depending on your system, you can compete in any of these power categories. Regional, the QSO parties are regional contests. The ARRL is a national contest, and there's international competition. You don't have to have the strongest station to win. All you got to do is play in the contest and submit your contacts, and they'll score you. I've actually won. Some of the people on here have actually won certificates for less than 5 contacts on a particular band. They just happen to be at the right place at the right time. So that's what the joy is in this, is you never know what you're going to get. You can work your rear end off and work 24 hours and do a personal best, and that's all you're going to get out of the contest. But there are times when you work 5 or 6 people and you get an award. Well, there's even more about this. What you do is you start out at a low level. You start out as a participant. This is to get to know you, yourself, and how your competitive juices are flowing. You make contacts, you improve your skill, you have fun, you help others win, because every time you make a contact with somebody, they're getting your score too. Then you can move up to an enthusiast level, and the enthusiast is you're enjoying the challenge, and instead of doing an hour in a 24-hour contest and feeling like you're drained, maybe you do 12 hours in a 24-hour contest, and you're chasing personal goals. You're adding to more contacts. You're utilizing the available time that you have to maximize your scores, and you're enjoying the challenge, or you become a real competitor level. And that's with winning records, peer recognition, full-time effort. Full-time effort, there are 4-hour contests, 12-hour contests, 24-hour contests, and 48-hour contests. I got to tell you, you're pretty drained after a 48-hour contest. You start seeing visions of things that you never thought you'd do sitting in a chair. And I got to tell you, the bathroom runs are short, but they're necessary. All right. The whole thing about contest is keep calm. It's just a game. Really, what it is to have fun and know the rules. It's really important out of all of this stuff to read the rules going into a contest so that you're not surprised by anything. You're giving the right exchange, and that's really the key. You're doing the right things to be ready for the contest, and so I'll give you those quick tips to get ready, to be ready to join your first contest. You don't have to be fast. You don't have to be expert. You just have to have enthusiasm. How well do you know your station? What your station means is your software and your hardware. Your radio, is it connected to your computer? Are you hand logging, or are you using an automated log system? What you see behind me on my little icon back here is my station. And what I have is I actually have 3 monitors, and I have a couple of different, I have a radio and a couple of different antennas that I'm using, and antenna rotators and things like that. You don't have to have all of that. I started out with a single dipole antenna and a radio. and had a great time up until I started to progress and improve my skill and wanted to do more. Then it became an addiction. My name is Don, K6GHA, and I am an addict. Okay, so I got that out of the way. All right, now, what else do you need to know? Well, you have to be ready and you have to have a strategy. You know, what is the category that I'm going to go in? What is my goal? Is it a personal goal? Or am I actually going shooting for what the guy did last year to try and beat the guy's score that was there last year? You have to know what your goal is. Be efficient. Short exchanges are good. You'll find that to be true in a lot of amateur radio, particularly in areas and things like that, where you have short exchanges. People tend to fill in where they shouldn't fill in. For instance, if I'm giving you, and I'm supposed to give you my exchange of my power, my signal report, and my name, what's the right order? Well, in certain contests, the order matters. You want to give the signal report, you want to give your name, and you want to give your power. And so what it would be 599 Don, 100 watts. That's all you need to say. You don't need to say, oh, hi, I'm Don from California, and oh, I'm running a cool antenna, and I've got 100 watts, and you're sounding good, but you're not sounding good as the other guy sounded. That doesn't help out in a contest because your efficiencies are where you're going to end up making more contacts. So please, just get rid of that. Please copy, because they're trying to copy it anyway. They don't need to be told to please copy. Efficiency is key. Be accurate. Errors happen in logging, and your focus is on prevention of that. If you know certain things and you're listening for certain things, and someone says something different than what you expect, pay attention. The reason they're saying something different is because they're trying to give you a clue that something has changed. It may be that they're operating out of state, and you normally hear them from Kentucky, and they're in Tennessee this week. They might be giving you Tennessee, and you may already think they're in Kentucky after a while, or your software is telling you that they're in Kentucky. And they're going, wow, why are they in Tennessee this week? It's because they're operating to win in that particular location. People travel to do this stuff. Okay, be motivated. BIC counts. Keep pushing for an improvement. Does anybody know what BIC is? What BIC is butt in chair. And what that means is the longer you sit in your chair and the more effort you put into it, the more chances you're going to be at the right place at the right time to make that contact that's going to put you over the top at the end of the game. Just keep pushing and keep building your skills. Okay, common terms, I'm going to go through these pretty quickly. S&P, search and pounce, it's spinning the dial to make your contact. You're not sitting on a frequency, you're not calling CQ. Running, that's where you sit on a frequency and you call CQ. CQ worldwide, this is Kilo 6 Golf Hotel Alpha. CQ worldwide, Kilo 6 Golf Hotel Alpha. You wait for somebody to call you. Searching and pouncing, you're listening for that person calling CQ, and you're going to jump in there and just give them your call sign and make the exchange. Pile up. Well, when the person who was giving the presentation earlier said, oh, how do you hear all these call signs? Well, in a competition, you hear, in some cases, when you call your call sign under a CQ, you may have 10 to 15 people trying to contact you. And you have to hear and sort out that. And there are techniques for doing that. You could say, if you heard a Kilo 5 and then it went blah, with a bunch of noise of everybody else, you could say Kilo 5 station again. Or if you heard ending in Zulu station, or you can segment it by zone by saying 5 stations only, give me your call. That way it cuts out everybody with a 6, 7, 8, 9, 0, 1, 2, or 3 or 4 in their number. So you're focusing down. So it's a technique to manage that pileup. You learn those things. Again, this takes time. It's not something that you're going to learn overnight, but it's exciting. To me, it's the next best thing to being in a true competition. A lid, that's not what you're going to be, because you're already taking my course, so you know this stuff. You know what you're in for. You're going to be practicing. You're going to be reading the rules, and you're going to be a good operator. All right, and a QSL. Don't use Q codes if you don't have to use Q codes. If you mean to say I copy you, say Roger. That is the international way of acknowledging what you have just heard. Don't say QSL. Don't say QRM. There's a lot of QRM on the frequency. Just say repeat. Do the simple things to make your efficiencies improve. Okay, I'm telling you techniques without ever getting involved in this. And the reason I'm doing that is to show you there are a lot of different facets, but there are also a lot of different tools that you can use. There are things that you need to know in HF when you get into HF, like how well can I talk to China right now? Well, it all depends on propagation. So what you'll have is you'll have propagation maps that will tell you from this location, here's where I can talk and probably be heard. And this is due to the radiation, sunspots, and everything else that are going on in the ionosphere, bouncing and different frequencies that you can use. And depending on your frequency, and you can see the frequencies up here, the megahertz frequencies that are being used by color, it tells you at this particular time, this is what might be open to you. So that instead of pointing your antenna over up to the north, up to Greenland, you're pointing your antenna down into the Pacific because you know you're going to have a better chance of making a contact. Now, that's just one of the things that you should look at. The other thing is you can map your contacts, or you can see what other people are contacting and making contacts on. This is called like a whisper net or something where somebody's putting out a very low signal and other stations that were receiving that signal are reporting on it. So they can actually see when you can talk right from New York all the way over the pole and come right down in the middle of China and Shanghai and make a contact. That person made a contact. That means it might be open to you. But if you're not in New York, then you have to see what's available here. And oh, look, Australia is open on this band and this frequency. So that's where you start to look and you learn how to read what's out there. What you see in my picture again is right behind my head is a blue map. This is a spectrum analyzer that's telling me here's a frequency of calls. Here's what you want to look at. This is where a person is calling or that. It allows me to dial in faster and hone in on that particular signal and try and figure it out. Okay, got to keep moving here. I'm going to give you some quick final thoughts. Is contesting is a game, and you get better with it with practice. I've been contesting now since about 2007, I guess, and it's allowed me to travel to Germany. It's allowed me to meet people on 100 watts in Mumbai, India, in Madagascar, in unique places. I've talked to the Antarctic. I've even talked to the International Space Station. That wasn't a contest. That was just DXing in that. But you can see that there's a whole world out there of adventure. Keys to our equipment knowledge. Know what type of equipment you have. You can play in VHF, UHF contests with your handheld if you want to. Just you got to know the rules and you got to know the contest, and it can be a lot of fun. Antennas, and I'm going to just say the bigger the better. I'm going to use that analogy because yes, the more efficient your antenna and the higher you put your antenna, the better things are on HF. Location, it's like real estate. Location, really important. If you're down in a valley in the bottom of a swale, your signal isn't really going to get out. But if you're on top of a hill, like on top of Half Dome in Yosemite, you're going to get all the way across the United States and over into Europe without a problem. Let's see, what do I have next? Yes, your self-improvement. Get to know yourself. What is it that motivates you? Work on that motivation. Work on getting better at what you do. And of course, these are the keys. Be prepared. Make sure you're prepared. Be strategic. Know if choose a category or an operating way that you want to be that you want to compete in, but you know that you're going to be competitive, be efficient, be accurate, be motivated. Those are really kind of the fun things. But most of all, really the whole idea of this is to have fun. I used to race sailboats. I've done some competitive other activities, but I'll be honest with you, I can't do a lot of those anymore. From a physical standpoint, I can't compete with the whippersnappers. But I got to tell you, with amateur radio, I'm still in the game. I'm having fun, and there are guys that are 80 years old, 90 years old that are still competitive and actually world-class operators in Morse code, in different forms of this that make them standouts and amazing people and fun to talk to. So how do you talk to these people? How do you get more information about this? Well, there's an upcoming event. There's something called a DX convention. It'll talk more about DX activities that happen. It's the International DX Convention. It is going to be a virtual meeting this year. It's going to have topics like de-expeditioning. It's going to talk about logging software. It's going to talk about the solar cycles, all this propagation nonsense that I've just been talking about. It's going to talk about different DX activities and contesting. Also, it's going to talk about equipment, different equipment that you may want to look at and find out more about. Sign up for it. They're giving away $500 certificates almost every hour. So you could be a winner if you just sign up for this thing and use that $500 to build your HF station if you want. Now there's other things that are going on as well. If you really want
to, excuse me, we're out of class time, but I don't want to cut you off. It seems like you have a lot more good stuff to say. If anyone has to leave the class now that it's 9 o'clock, go ahead. But stick around. We'll leave the Zoom link up. And if you have questions for Don, he will certainly answer them.
Absolutely.
And please continue, Don.
And I'm really apologetic. I was trying to get it in before 9, but I get too enthusiastic. All right. There's also something called Contest University that you can sign up for free. Again, this happens during midweek on a Thursday in May 20th. But these are the kind of things from international contesters. So you're going to learn more about contesting as well, about what that is for them. Okay. Again, bottom line is we can't cover everything about contesting, but I can give you that flavor of if you have a competitive gene, here you go. This is your opportunity. So here's some great references. Amateur radio contesting for beginners. Look on Amazon. Amazon has some books. There are videos about what does it mean to do contesting. There's ARRL, and they have your passport or your passport and guide to radio sport for beginners. It's a document that you can get as well. There are loggers, event calendars. You can share your results once you do a contest with others, and there's great resources out there to do that. So, I mean, get out there, get the bug, have some fun, and be like I am over the weekend where I'm pretty much exhausted, but I keep going because you gotta figure out a way to keep going after 24 hours, and you'll eventually you'll have that satisfaction of knowing that you can outlast even the good guys. All right, I really wanted to say thanks, and sorry I took so long, but I'm really happy to answer any questions you may have regarding contests. Yeah, again, yeah, this is I see the notes in there. I was talking a lot about HF frequencies and shortwave, that kind of thing, but there are VHF and UHF contests. Matter of fact, in 2 weeks, there's one early June, there's one coming up where you could get on your handheld and just join in. There's a local guy that would love to get you in his log because you would help him once you get your license, you would help him win that contest. All right.
Questions for Don?
Did I blow your minds and make you feel like you're overwhelmed with information?
We already did that.
Oh, okay. In that case, I'm pouring it in your ear and just letting you know there are a lot of different avenues that you can take and search for in amateur radio. I happen to find one that I absolutely am passionate about. I'm getting better at, but I aspire to be as good as my mentor, but I don't know that I'm going to get there anytime soon, because he can operate two CW stations simultaneously, one in each hand, and talk to people at the same time, and talk on a third radio at the same time. So that's where he is. I'm not quite there. I'm a single tasking individual, but I still do okay. I still have fun.
Well, thanks, Don. You certainly conveyed your enthusiasm for contesting, which is great. So one aspect of amateur radio that many people don't know very much about, and a lot of people have a lot of fun. And if you're good at contesting, you will also be good at disaster communications, because you learn to extract a lot from a very weak signal.
That's John, that's really well said. It is really hard sometimes in a pileup to pick out the people that you really want to work. There are certain folks that you're searching for. So you listen for certain characteristics, like a double number in their call sign, or a unique identifier like a P in front of their number. Those are all unique things, and you'll start to get an idea of the grid around the world of where they're calling from. And so you're constantly listening for them, because you know that they're going to be the best value for your contact. So again, thanks for giving me the opportunity. I hope you guys have found this to be fun. It is once you dive into the deep end of the pool, but getting to the deep end of the pool is right after you get through this class and get your certification. And then it's going to be really fun. That's all I got to tell you, is it gets better.
Okay, that concludes our class for today, unless anyone has any final comments or questions. All right, we will see you next week, same time, same Zoom link, and we will continue.
Thank you.
Bye, everybody.
Guys.
Good luck, guys.
Good night.
Good night. Thank you.
You're learning from
Good
John.
night.
You're
Thank
going to be
you.
great.
Hey, Don, are you still there?
I'm here.
Hey, no, Don. I was saying Don.
He jumped off. It looks
Don and
like.
John. Don's gone. I just wanted to tell him you did a great job. I came in late, but I'm outside, so I'm all dark.
Yeah, I was going to say you're Zooming by candlelight.
Yep, by cell phone light.
Oh,
Good
very
night,
good.
everyone.
Good
Yes.
night, Roberta.
Good night.
Good night. Thanks for your help, Karen. Good presentation.
Oh, thank you.
Excellent.
You did great as usual, John.
Thank you.
Excellent. It was all good after I got here. Sorry I was late.
No problem. All right, I'm gonna kill the link. Good night, everyone.
Yep. Good night.